Chemistry is the science of stuff. It studies what things are made of. It looks at their properties. It explores how they change. This field is truly fascinating. It helps us understand the world around us, from the air we breathe to the food we eat. Even the clothes we wear involve chemistry. It is a central science. It connects physics with biology. It links geology with environmental science. Chemistry is everywhere. Think about a simple glass of water. Chemistry tells us water is H2O, 2 hydrogen atoms, 1 oxygen atom. These atoms are joined together. Chemistry explains why ice floats. It explains why water boils. It even explains why water can dissolve sugar. These are everyday observations. Chemistry provides the reasons behind them. This understanding is powerful. It allows us to manipulate materials. We can create new substances. We can improve existing ones for our benefit. Consider the medicines that heal us. Pharmacists and chemists develop these. They understand how chemicals interact with our bodies. This knowledge saves lives. It improves our quality of life. Think about the fuels that power our cars. Petroleum chemistry is complex. It involves breaking down large molecules. It involves reforming them into useful fuels. This entire process is pure chemistry. It powers our modern world. Without it, transportation would be vastly different. Chemistry also helps us solve big problems. Climate change is a huge challenge. Chemists are working on solutions. They develop new ways to capture carbon dioxide. They create more efficient solar cells. They design better batteries for storing energy. These innovations are crucial for a sustainable future. Understanding chemical principles is key. It allows us to tackle environmental issues. It helps us protect our planet for future generations. Chemistry holds many answers. Atoms are the basic building blocks of all matter. Imagine them as incredibly tiny Lego bricks. Everything you see and touch is made of atoms. They are so small. Millions could fit on the head of a pin. Each atom has a central core. This core is called the nucleus. The nucleus contains protons and neutrons. Protons have a positive electrical charge. Neutrons have no charge. They are neutral. This structure is fundamental. Surrounding the nucleus are electrons. Electrons are even smaller particles. They have a negative electrical charge. They orbit the nucleus in specific energy levels or shells. Think of planets orbiting a sun. The number of protons in an atom's nucleus is very important. It determines what kind of atom it is. This number is called the atomic number. For example, an atom with 1 proton is hydrogen. An atom with 6 protons is carbon. This defines its identity. An element is a pure substance. It is made up of only one type of atom. All atoms of an element have the same number of protons. Hydrogen is an element. Carbon is an element. Oxygen is an element. There are many known elements. Scientists have discovered over 118 of them. Some elements are very common. Think of oxygen in the air, or silicon in rocks. Others are very rare and sometimes man-made. These elements are the ingredients for everything. Each element has unique properties. Gold is shiny and does not rust. Iron is strong and magnetic. Helium is a very light gas. These properties arise from the structure of their atoms, specifically the number of protons and the arrangement of electrons. Understanding elements is crucial. It is the foundation of chemistry. We use these elements to build everything, from simple molecules to complex machines. They are the alphabet of the universe. Molecules are formed when 2 or more atoms join together. They are held together by chemical bonds. Think of atoms as individuals. Molecules are like groups of friends holding hands. These groups can be small, or they can be very large and complex. Water is a simple molecule. It has 2 hydrogen atoms. It has 1 oxygen atom. Its chemical formula is H2O. This formula tells us the types and numbers of atoms in the molecule. It is a chemical recipe. Molecules can be made of atoms of the same element. For example, oxygen gas in the air is O2. This means 2 oxygen atoms are bonded together. Nitrogen gas is N2. 2 nitrogen atoms are bonded together. Molecules can also be made of atoms of different elements. Carbon dioxide is CO2. 1 carbon atom, 2 oxygen atoms. Table salt, sodium chloride, is NaCl. 1 sodium atom, 1 chlorine atom. These combinations create new substances with new properties. The properties of a molecule are different from the properties of its individual atoms. Hydrogen is an explosive gas. Oxygen supports combustion. But when they combine to form water, H2O, they create a liquid. This liquid can extinguish fires. This is a remarkable transformation. The way atoms are arranged in a molecule is also important. This arrangement is called its structure. The structure affects how the molecule behaves. It influences its shape and reactivity. Understanding molecules is key to understanding chemistry. Most substances we encounter are made of molecules. The food we eat contains complex molecules. Carbohydrates, proteins, and fats are all large molecules. The plastics we use are made of long chains of molecules. These are called polymers. Medicines are often complex molecules. They are designed to interact with specific molecules in our bodies. The study of molecules is a vast and exciting field. It drives much chemical research. The periodic table is a chart of all known elements. It is one of the most important tools in chemistry. It organizes elements based on their atomic number. It also groups them by their chemical properties. Dmitry Mendeleev, a Russian chemist, created an early version. He noticed patterns in the properties of elements. He arranged them so elements with similar properties fell into columns. This was a brilliant insight. He even left gaps for undiscovered elements. The table is arranged in rows and columns. The rows are called periods. Elements in the same period have the same number of electron shells. As you move across a period from left to right, the atomic number increases. This means atoms gain more protons and electrons. The columns are called groups or families. Elements in the same group have similar chemical properties. This is because they have the same number of electrons in their outermost shell. These are called valence electrons. The periodic table provides a lot of information about each element. It shows the element symbol. For example, H for hydrogen, O for oxygen. It shows the atomic number. It usually shows the atomic mass as well. Some tables show electron configurations. They might show electronegativity values. All this information is incredibly useful to chemists. It helps them predict how elements will react. It helps them understand trends in properties. It is like a map for chemists. The periodic table is not static. New elements have been discovered or synthesized over time. These new elements are added to the table. The heaviest elements are often radioactive. They are usually made in laboratories. They exist for only very short periods. The table helps us understand the fundamental building blocks of matter. It shows the relationships between them. It reveals the underlying order in the universe of elements. It is a testament to scientific discovery. Section 5. The ties that bind understanding chemical bonds. Chemical bonds are the forces that hold atoms together in molecules, or they hold ions together in crystals. Think of them as the glue of the chemical world. Without chemical bonds, matter as we know it would not exist. Atoms would just float around individually. There are several types of chemical bonds. The main types are ionic bonds and covalent bonds. Metallic bonds are another important type. Each type involves electrons in different ways. Understanding these bonds is fundamental. Ionic bonds usually form between metals and nonmetals. In an ionic bond, one atom loses electrons. It becomes a positively charged ion, or cation. Another atom gains those electrons. It becomes a negatively charged ion, or anion. The positive and negative ions are then attracted to each other. This attraction is the ionic bond. Table salt, sodium chloride, or NaCl, is a classic example. Sodium or Na loses an electron. Chlorine or Cl gains an electron. They form Na+ and Cl ions. These ions form a crystal lattice. Covalent bonds usually form between nonmetal atoms. In a covalent bond, atoms share electrons. They do not completely transfer them. By sharing electrons, each atom can achieve a more stable electron configuration. Water, or H2O, is a good example. Each hydrogen atom shares one electron with the oxygen atom. The oxygen atom shares one electron with each hydrogen atom. This sharing creates strong bonds. Many common substances are held together by covalent bonds. Methane, or CH4, and carbon dioxide, or CO2, are other examples. Metallic bonds are found in metals like copper wires or iron bars. In a metallic bond, electrons are delocalized. This means they are not associated with a single atom. Instead, they form a sea of electrons. This electron sea surrounds a lattice of positive metal ions. This sea of electrons is free to move. This explains why metals are good conductors of electricity. It also explains why they are malleable and ductile. They can be shaped without breaking. These bonds are crucial for many materials. Section 6. Transformations everywhere. Chemical reactions. A chemical reaction is a process. It involves the rearrangement of atoms and molecules. This rearrangement forms new substances. The original substances are called reactants. The new substances formed are called products. During a reaction, chemical bonds are broken in the reactants. New chemical bonds are formed in the products. This is the essence of chemical change. It is different from a physical change. A physical change, like melting ice, does not create new substances. Water is still H2O. There are many types of chemical reactions. Combination reactions occur when two or more substances combine. They form a single new substance. For example, iron and sulfur can combine to form iron sulfide. Decomposition reactions are the opposite. A single compound breaks down into two or more simpler substances. Heating mercury 2 oxide causes it to decompose. It forms mercury metal and oxygen gas. These are fundamental types of transformations. They happen all around us. Single displacement reactions involve one element replacing another element in a compound. For instance, if you put a piece of zinc metal in copper sulfate solution, the zinc will replace the copper. You get zinc sulfate solution and copper metal. Double displacement reactions involve the exchange of ions between two compounds. When solutions of lead-2, nitrate, and potassium iodide are mixed, a yellow precipitate of lead-2 iodide forms. This is a common way to make new ionic compounds. Combustion reactions are another important type. They usually involve a substance reacting rapidly with oxygen. This reaction produces heat and light. The burning of wood is a combustion reaction. So is the burning of gasoline in a car engine. These reactions release energy. This energy can be used to do work. Understanding chemical reactions allows us to control them. We can synthesize new materials. We can generate energy. We can explain natural processes like digestion or photosynthesis. Chemistry is truly dynamic. Section 7. Historical footprints. Key moments in chemistry. The journey of chemistry is long and fascinating. Ancient civilizations already practiced early forms of chemistry. They used fermentation to make wine and beer. They extracted metals like copper and gold from ores. They made glass and pottery. These were practical arts. They were based on observation and trial and error. The ancient Greek philosophers also thought about matter. They proposed ideas like atoms. But these were philosophical concepts, not based on experiment. This was the dawn of chemical thought. The Middle Ages saw the rise of alchemy. Alchemists had several goals. They tried to turn base metals like lead into gold. They searched for the elixir of life. This elixir was supposed to grant immortality. While they did not achieve these grand goals, alchemists made important contributions. They developed many laboratory techniques. They discovered and purified new substances. Distillation, crystallization, and sublimation were refined during this period. Their work laid some groundwork for true science. The 17th and 18th centuries marked the birth of modern chemistry. Scientists like Robert Boyle studied gases. He proposed that matter was made of tiny particles. Antoine Lavoisier is often called the father of modern chemistry. He emphasized careful measurement. He established the law of conservation of mass. This law states that mass is neither created nor destroyed in chemical reactions. He also identified and named oxygen and hydrogen. His work transformed chemistry into a quantitative science. The 19th century was a period of rapid advancement. John Dalton developed his atomic theory. He proposed that elements are made of atoms. He said atoms of different elements have different masses. Amadeo Avogadro proposed his hypothesis about molecules and gases. The periodic table was developed by Mendeleev. Organic chemistry, the study of carbon compounds, blossomed. Friedrich Wöhler synthesized urea, an organic compound, from inorganic starting materials. This shattered the idea of a vital force needed for organic compounds. These were revolutionary times. Section 8. Chemistry Today. Modern Marvels and Innovations. Modern chemistry is an incredibly diverse and dynamic field. It continues to push the boundaries of knowledge. It solves real-world problems. One major area is materials science. Chemists are designing and creating new materials. These materials have specific, tailored properties. Think of lightweight composites for airplanes, or flexible electronic displays, or biocompatible materials for medical implants. Nanotechnology is a key part of this. It involves manipulating matter at the atomic and molecular scale. This opens up amazing possibilities. Pharmaceutical chemistry is another vital area. Chemists play a crucial role in drug discovery and development. They design molecules that can interact with biological targets. These targets are often proteins or enzymes. The goal is to treat diseases. This involves complex synthesis. It involves understanding how drugs work in the body. Computational chemistry is increasingly used. It helps predict molecular properties. It speeds up the drug design process. New medicines are constantly being developed. Environmental chemistry focuses on understanding and mitigating human impact on the environment. Chemists monitor pollutants in air, water, and soil. They develop methods for remediation. This means cleaning up contaminated sites. They are also working on green chemistry. This aims to design chemical products and processes. These processes reduce or eliminate the use of hazardous substances. This includes developing renewable energy sources. Fuel cells and advanced batteries are examples. Sustainable chemistry is essential for our planet. Analytical chemistry is the science of measurement and identification. Analytical chemists develop and use methods. They determine the composition of substances. They can detect trace amounts of chemicals. This is crucial in many fields. Food safety relies on it. Forensic science uses it to analyze evidence. Medical diagnostics depend on it for blood tests. Advances in analytical techniques like mass spectrometry and chromatography allow for incredibly sensitive and precise measurements. This underpins much of scientific progress. Section 9. The Unseen Architect. Chemistry in our daily lives. Chemistry is not just something that happens in laboratories. It is an integral part of our everyday existence. It is the unseen architect shaping our world. From the moment we wake up, chemistry is at play. The soap we use is a product of chemical reactions. So is the toothpaste. The clothes we wear are made of fibers. These fibers are either natural polymers like cotton or wool, or they are synthetic polymers like polyester or nylon. Both are understood through chemistry. Their properties are due to their chemical structure. Consider the food we eat. Cooking itself is a series of chemical reactions. When we bake bread, yeast performs fermentation. This produces carbon dioxide gas, making the bread rise. The browning of toast is the Maillard reaction. This is a complex set of reactions between amino acids and sugars. Digestion is also a chemical process. Enzymes in our body break down large food molecules. They become smaller molecules that our body can absorb and use for energy. Chemistry powers our bodies. Think about technology. The smartphone in your pocket is a marvel of chemistry. The battery uses electrochemical reactions to store and release energy. The screen is made of special glass and liquid crystals. The microchips inside are manufactured using highly precise chemical processes. The plastics in its casing are polymers. Even the vibrant colors on the display are due to specific chemical compounds. Without chemistry, modern technology would be impossible. It is the foundation of these devices. Furthermore, chemistry plays a vital role in addressing global challenges. Developing new ways to produce clean water involves chemistry. Creating more sustainable agricultural practices relies on understanding soil chemistry and fertilizers. Fighting diseases requires the design and synthesis of new medicines. As we look to the future, chemistry will continue to be essential. It provides the tools and knowledge. These are needed to improve our lives. They help us build a better, more sustainable world for everyone. Chemistry is truly fundamental.